have to go back a little bit. So we did the assumption checks. And again, these are the types of things you have to do in the exercise and your assignments. And the more you do it, the more you engage with it, the easier it will become. Trust me, just like a matter of keeping at it and doing it. So some of the things you might have already come across, but it's important to bear in mind different types of notations. So plus indicates the inclusion of an explanatory variable, so it's not just summing. So if you have formula expressions, they're different than just your calculator, right? So it's just telling you that you can have plus to add something, minus to delete something. So remember -1 when we deleted, for example, the intercepts from regression models. So when we standardized everything, we had to remove the intercepts, and we used -1 to say don't use the intercepts in those types of models. And this is the one we care most about. So this is the interaction term, and then this slash means that there's nesting. You likely won't have that, but in case you have nesting, that's the type slash, and this means conditioning on a third variable. So that's just some things. You come across these things in formula, and you'll come across them when you have to write expressions, also in multi-level models, which we'll tackle later. So a factorial Anova with a three-way interaction would just be n times p times k, and so that would just be so n, p, and k are two-level factors here. So that would have all the three-way interactions. So you don't have to say n times p plus n times k plus n times pk. So you don't. If you do this, it will automatically do all the underlying two-way interactions and main effects. Yeah? Everybody understands this? So sometimes you want a three-way Anova, but you don't want the three-way interaction fitted. And so in that case, that's the formula to make sure that it fits all the two-way interactions, but not the three-way interaction. So in that case, all the two-way interactions are n times p, n times k, and then p times k will be in your model, but not n times p times k. That three-way interaction will not be part of your model. Yeah? So those are the most common things which you'll need. So it's important that if you fit a three-way interaction, all the lower level effects should be in there. So if you're interested in studying the three-way interaction, all the lower level things have to be in there. If you're doing a two-way interaction, all the lower level main effects should be in there. Otherwise, it's not interpretable. Yeah. So when you're testing a three-way interaction, you would include all the two-way interactions and all the main effects. So how would you go about doing the interaction? So you've done this first part. You've also perhaps managed to set a factor for those. And in order to get the same type of results as SPSS, because that might be what you're after, so those type 3 contrasts, you can do options contrasts and then put this chunk in, and this will change the default from type 1 to type 3, which is what you want in order to make them comparable. So again, SPSS uses type 3, and R uses type 1 by default. And what happens then is that we do this, and then Anova. So this is part of the car package which you've used before, and then LM, the formula, so the multiplication type of thing. So supplement times dose, and then you have to tell it where the data set is, and then the type of errors we want, which is 3. Yeah. So it's the same as the formula we've seen before for in lecture 3 for Anova, but now we have this multiplication term, which will fit all the interaction effects. What you then get is a results type of table, and in this case we find a significant interaction. Yeah, so again it stars the effects, and again in some cases if you had a type 2 type of if you had used type 2 errors, then those would not necessarily be interpretable, but in a type 3, because it's marginal, you can also interpret those main effects. Yeah. So beware on the type of error you use influences how interpretable the main effects are. Any questions? So there's always a gazillion other ways to do it, and I'll tell you about some of the ways of doing it. So you can also just use a linear model, but then you have to again use the drop one type of thing, so it will print the coefficients, but you won't get your F tests. And again, go back to the slides from week 3 to see how to use it using the lm command without using the car and Anova things. So if you use lm and then use drop one, you can get the F type of tests corresponding. And again, you have to set the contrast first. But this will print you the coefficients and not the F tests, because that's what the linear model does. So if you then use the drop one command, it will give you the F tests, and these are the same type of values that we had before. But some people like not having to load the car package, and some people, so that's how you would do it with just base R. If you forget to load the car package, this route should always work. Yeah, so it's the same type of values which we had before. Now, again, one of the easiest ways to do it is to use the easy package, and as you remember from last time, it will automatically print some of the tests. So it will automatically print Levine's test and will print some other things already for you. Not always, but where it can. It uses a different type of notation, and you need an ID variable. Because there is no ID variable, we have to make one because the easy Anova package can do all sorts of data formats, and sometimes you will have a line of data corresponding to every trial which a person did, rather than it being a guinea pig. So that's why you would need to say these data belong to the same type of person. And so in this case, it's quite easy. You should remember from the first thing. So we have 60 guinea pigs. So this will just put 1, 2, 3, 4, 5, 6. This will make a new variable with their ID, which is just a running number going from 1 to 60. It's a sequence that we use. And we need that to feed it to Easy Anova here, because we need that ID variable for the WID command. And that's because this package does both, there's all sorts of Anovas. It does between, within, but it also does complex block designs, so it needs to know which parts are part of the same person or guinea pig in this case. So that is how you would do it. So you would specify the data set it has to look for, the dependent variable, use the dot to notate where it is, the WID, and then the between things. And if you leave any type of, so by default it will always do a full factorial, so it will always calculate all the interaction effects. And then you can say, give me an object to return. So that's just this return AOV command. And then we want detailed information if we can get it. And again, there's many other things you can tweak, and you have to look at the easy manual if you want other things. But the important thing again is to specify the type of errors you want. And type 3 is what we're after if we want to compare to SPSS, and if we're very interested in the testing the interaction effect. So it will print a lot of output there. So it's done a Levine's test for homogeneity of variance. And that should have corroborated what you would have done with 2 separate Levine's tests of homogeneity of variance. You shouldn't have found a problem. It will print the formula and some sums of squares and residuals below here. But what we're mostly after is, again, these are the same type of F values that we had with the other roots, but it's printed now and with like the E notation, but you have a stars for significance. So it's the same type of results that we got before. And again, these guess is the generalized attest squared. So you also get this type of effect size measure already from this thing. Again, you can calculate it all by hand, so you can make a table with the means and standard deviations and calculate Cohen's d or of some sort. But the nice thing is that here you already get a measure for effect size for the interaction. So 0.113, what do people think? Is that a large effect or a small effect? What would be a large effect? What would be the largest effect possible? Are you pointing or just touching your hair?
One's a large.
Yeah, one is everything is explained by this interaction effect. So 0.13 is okay, but it's not a very large effect. Yeah. But most effects in psychology won't be very large. But you should bear in mind that this is a generalized eta squared and not a partial eta squared. So it's a better effect size measure, and so the partial is after partialing out, and so all the partials don't add up to 1, but all the generalized effect squares do add up to 1. In a nutshell. So again, one of the key benefits is that you can export certain things already, and then you can get these customizable tables, which will hopefully save you some time when you actually have to do your reports. So if you want to make it prettier, you would change some of these things. The easiest routes, if you want exportable tables, is to use the car or the easy objects routes rather than using the LM objects. And again, you use Stargazer, and I've just made 2 examples of how to do it. And we need summaries false because it treats it as a data frame, and otherwise it will start calculating the mean, standard deviation, and modes, and we don't want that. And we say which type it is, and then we have to say what the output is, and just to show you that this sort of works. So this is the an example of so obviously you would be able to further beautify it. So if you want different types of labels, because it's a data frame, you can use names and you can change all the labels and then print it. And so it doesn't say pre or larger than f, but it says. But then again, you could also do that in Word if you really want. But if you have to do this often, you can write some code, and then you would never have to do that again, and never have to edit that again. And so these are the outputs from the F test, and it's done some of the rounding also. So that was for the car object, and this is for the easy Anova. So it's done the same type of things. It's printed the p-values. So it only uses 1-star notation, like sometimes in journals 2 stars means but this one only puts in a star for one significance. And it's printed as also this effect size measure. And again, you can customize everything by changing the object. So because it's a data frame, you can change all the names to it. So you can change all this, you can change all this, and then export it. And so then you already have a formatted results table for everything. Again, the reason why you want to do that is if you have to do this often for reports, it will save you time. And the other reason is that it will reduce the amount of errors you make, rather than copying and pasting between different programs or manually doing the rounding. So trimming away the decimals. This is all. You didn't touch anything. You can blame Stargazer in case it goes wrong. Yeah. Any questions? So, how would you write up that type of results? Obviously, you might not write about guinea pigs because you deal with students or people, but you would write up a two-way Anova was conducted to examine the effect of supplement and dose on growth of odontoblasts, which are these tooth-growing cells, or tooth-growing cells or tooth growth. There was a significant interaction effect between supplement and dose, and then these are the F characteristics, so the degrees of freedom from that table, the value, the significance, and then I've added the effect size because I think that's good practice. So, yeah. Any questions? So you should have these are the type of things you will also do for reports and for other things. What you would then do is, as Dana already mentioned, you would then do post-hoc tests or post-hoc things to see where the effects lies. But most of the times, people would also do that visually. So you would plot the results, and then you can sort of see where it's what is going on, to just find out what's happening. But you can do the post-hoc test via again QPHSD. So that's what the same type of command we had for Anova, and then you can say which one you want. And you could also do that for the interaction effect, so you just label which one you want. And you can, again, there's an alternative of doing this, and you can again do it this way via multicomp, which we also saw when we talked about Anova. And again, it will print with significance tests. And again, there's many different options, so you might have heard of Bonferroni, Tukey. So have a read about all those different types of contrasts, and then take the one which you think is most suitable for your analysis. I do that beforehand rather than post-hoc. So how would you plot the interactions? And because some of you might still struggle with ggplot, there's actually something which makes it even easier, which is ggpopr. and that has some things already built in to make relatively pretty graphs. And so here we're going to make a violin plot, and we're going to add a box to it. And so when I say violin plots, I usually mean it has a box plot attached to it. But geom violin is just the shape, and geom box is the box plot. And we're going to overlay the points so we can sort of see where the points lie. And we use jitter to make sure that it's that not all the points are lying on the same thing. As you might recall from when we did scatter plots, we want jitter to sort of jumble the points somewhat. So when we fit a line through it, that we're able to see what's going on rather than all the points being in the same place. You could omit jitter perhaps if you have not a lot of points on the same things. So because it's only 60, but if you have like large databases, then usually you want to add jitter. So this is GG violin, and then the data sets, the X, the Y, the color we want to color by. We can pick a palette, and you can. You've seen some examples where I've picked accent or dark tone, and it will just pick from this range. But you can also specify custom colors. So here I want black, dark blue, dark red, and you can read more about which type of colors. But you can have all the colors in the world from GG plot, and then you can say what do you want added. We want jitter, and we want a box plot, and we want the shape to be and not the shape of the violin plot, but the shape of the points to correspond to those. And then these are the labels we want, the color we want, and the shape we want. And that's corresponding to the labels. So we'll say dose with a capital letter and dose with a tiny thing. And then we want it to be wrapped by the supplement which they received, whether it's vitamin C or orange juice. So we want to have a panel plot with these 3 supplements, and we're hoping that will sort of show what's going on. And where did it go? That's a pity. It's not printing it. I had done it before and did print it, so I'll make sure that that's corrected in the graph. But there was going to be a beautiful graph where it's plotted. So that's it's probably here, but perhaps I told my slide thing to omit the graph. So I'll correct that. Sorry about that. So again, you can have the means and standard deviations exported, and that's so it's printed the table here, but it's again in a Word document, and you can use APA table and then use APA two-way table. So we've done that for a one-way table previously. And it's the same type of command as before. Supplement, dose, length, tweet growth, file name. You can number it. You can say you want it landscape or you want it horizontal, and you can say you want a confidence interval or not. And so that's the lower limit, upper limits. And you can also say give us the marginal means or not. And just to give you an example of what it actually then does. Where did it print it? There we go. It will have made this type of table and exported it, and then you can copy that directly or edit it further. So it's done the doses, it's done the means and the 95% confidence intervals and the standard deviations for you. And yeah, and that's quite handy, so you don't have to do that all manually. I think here I exported it as text actually rather than as a Word document, because I didn't put .docx at the end. But yeah, so I did. So it was not as beautifully formatted perhaps, but I made it a text file rather than a Word document. So if you put .doc or put .docx, it will make it a Word document. But you can sort of see what the layout would be also when it's printed here. Again, you can bootstrap everything in R, and again, the reason you might want to do that is because some of the assumptions are violated. It's the same type of function you've used before, also perhaps in the exercises. But the key thing that changes now is that we use this type of command, and we call the contrasts in between. And we also have to have this in singular case true, and that's because sometimes things won't converge. and we want the Bootstrap then to continue and not just go, I completely messed up and I can't proceed. So it's really important that you don't forget the singular.ok is true statement, because otherwise it won't work. That will happen especially in small databases, because there might be cases where you're so unlucky you've sampled the same guinea pigs in your set, and there's no standard error or no variance. And if we do that, if we take large amounts of samples, you might be unlucky enough to have a sample where it's the same person or same guinea pig for the entire 60 cases, and that means there is no error to it because it's the same type of value. Or if it's true that it's a very low error and can't calculate certain things because none of the conditions appear, for example. Because if everybody's, let's say, in the orange juice condition, so you've been very unlucky and you've sampled 60 cases, but they're all the orange juice ones, and you have none of the vitamin C ones. In that case, you can't calculate the factorial Anova because it doesn't exist. And that's why we need that type of statement. And here I've done it with thousands of cases. So that's the R, is thousands. And it's a similar type of function which you've seen before when we're doing the regression coefficients and the Anovas before. You can again look at the thing. So this is the original for the p-value. And then we'll give you the bias and the standard error. And then we can get the 95% confidence interval from all these bootstraps for a p-value. And I pick 89%, 90%, 95%. You can pick sometimes what you want. And this is the 98% confidence interval, so it goes from very low to quite high. And again, it's the same type of command you've seen before. And that's all I have to say about that. There are ways to automate certain type of things, and this is quite cool. So you can build trees, and so you basically tell the computer to find the interactions for you, and you need a package called tree, and then you can say use all the variables in there and try to build me a tree. And has it done it? No. Again, it's not built a tree. So I think what has happened is I might have gone off the Wi-Fi, and that could be it. Let me just check.